Hello, everyone. You must have been listening to the course on principles of downstream processing. This has been a short course. We also have a long course, which is 40 hours in duration. This is a shorter course. It is meant for somebody who wants to quickly grasp some of the techniques related to the downstream. So it's been made into a 5 weeks program. I hope you enjoyed the course and you have picked up a lot of new techniques, and you have also picked up some of the design concepts that are being mentioned in this particular course. And so I have got a few questions as a feedback. I thought I'll just give a summary of the course contents, as well as try to answer some of those questions which have been raised by some of your participants. Okay, so okay, so we looked at many things during this short program. As I said, we also had a long program on this particular topic, which was 40 hours in duration. So I'll just cover very briefly what we have been gone through in the past 5 weeks. Okay, so as you know, downstream involves recovery, purification of a lot of products, bioproducts, pharmaceutical products, food, nutraceuticals, okay, health foods, and animal feeds. Nowadays, these are becoming very big. Nutraceuticals, health foods, animal feed are becoming a big area, and generally biological approach is being followed for that. Okay. So if you are talking about a fermentation or a biotransformation, generally we use a source from animal or plant or bacterial, and there is a fermentation taking place. Of course, downstream can also be used for chemical processes. In fact, it has been there much longer than biochemical processes. So many of those techniques, principles from chemical engineering is being adopted here as well in our biochemical processes. Okay, so as I have told you before, I think in the first lecture or second lecture, we have the reactor, that is the bioreactor. We have the fermenter, that's the heart, I would say. Then whatever is on the left-hand side is your upstream, where you are preparing raw materials, where you are preparing the biocatalyst, or you are preparing inoculum if it's a fermentation product. And on the right-hand side, we have this downstream. Okay, so we talk about recovery, purification, waste removal, waste treatment, side product generation. All these are part of the downstream, although not much importance is given for the waste treatment, because waste treatment is being discussed as a separate topic. We talk more about recovery and purification as the downstream. So we can use the same philosophy for chemical processes also. So this could be a chemical reactor, and recovering your product on the right and purifying it to very high degree purity. Again, in chemical engineering also same approach is followed. You may also have a recycle of the raw materials. You may have recycle of catalyst, that means the enzyme or a active cell. Okay, so all those could getting recycled. So the right hand side is what we have been looking at over the past 5 weeks, I would say. A lot of techniques are being followed: removal of solids, extracting or recovering your desired product, then purifying your product to a very high degree purity, because if it is a pharmaceutical product, you want it to be 99 plus purity, and so on. Okay, so if you look at this particular slide, I did show this slide before also. So we have the centrifugation, filtration. Okay, that's where you are removing the solids from the liquid, and then we have different ways of breaking the cell. If it's an intracellular, of course, you need to break the cell. If it's an extracellular, you don't have to bother much. Okay, then you have the centrifugation, filtration, and then we have a lot of recovery steps like liquid, solid liquid extraction, precipitation, dialysis, electrodialysis. And then, of course, you have a high degree of purity is desired. Then we go through chromatography, then we go through membrane. Okay, it could be a nanofiltration type of approach, or even RO, reverse osmosis approach. And then finally, if your product is a solid, you would like to crystallize it or lyophilize it. As you know, lyophilization is done at low temperature. So if it's a biomolecule, you would like to maintain the thermal lability of the particular material. And then finally, you go through drying. You can think of spray drying, like your instant coffee, or like your milk powder, or it could be a normal heated tray, which is a material which can take up temperature. Okay, so many different techniques, are being followed, and we talked about each one of them. In the course of these 5 weeks, we talked about what are the issues, what are the different design calculations one needs to do. Okay, advantages, disadvantages of each one of these technique, and so on, actually. Okay. Okay, so what do you need to consider when we design downstream? Cost. Of course, cost plays a very important role. The cost of the downstream, and the equipment cost. Okay, because equipments cost a lot of money. The piping, the instrumentation, the electrical, the cabling, wiring, all those costs. Then cost of operation. You are talking about using, if you are using steam, if you are using water, if you are using solvent, if you are using coolant, air, compressed air, oxygen, all these cost money. So we need to understand what's the cost of operation. And then safety, of course, is very important, because it's being worked with human. And when we talk about large scale operation in terms of 100,000 liters, then safety plays a very important role. Then comes green chemistry approach. This is a concept which has come in the past, I would say, 20 years. The idea is to minimize solvents, minimize waste, recycle solvent, recycle raw materials. So that's called recycling. And then using mild conditions at maybe atmospheric temperature, atmospheric pressure, and so on, mild. As you know, biological processes are generally done at mild conditions. So there is no problem about being a biological process being green. Of course, we also need to consider recycling and minimizing. Then environmental issues, how do you dispose the solid biomass? It could be cells, it could be solid biomass, it could be a genetically modified organism. So is it safe to dispose of in the open? Do we have to decontaminate? All these we need to consider, liquid, gas, and so on. So we need to consider all these aspects also when we talk about environmental issues. Then scale up. In the lab, we generally work at say 100 ml scale, but when you go to a large fermenter, I hope I suggest that all of you have a look at a fermenter on an industrial visit. Even if you go for a alcohol manufacturing, you'll see huge fermenters, 100,000 liters fermenter, 1,000 meter cube fermenter, very large fermenters. So moving up from 100 milliliter, going right up to 100,000 liters, 100 meter cube, 10,000 meter cube, and so on. So how do you scale up the entire process? How do you maintain the cells at the same conditions as they were in the small scale? Okay. Do the cells get enough oxygen when you scale it up to a very large scale? Do the cells get enough nutrients when they move up from small to large scale? So these are issues we need to consider, because if it's an aerobic process, we need to maintain the amount of oxygen sufficient for the microorganism, for respiration, and for its growth. Otherwise, the organism may die. Okay, so that's a very important aspect to consider. Then utilities. You may require steam, hot oil, hot water, chilled water, coolant, so many different utilities, gases, nitrogen. If you want to maintain, say, anaerobic condition, you may require CO2 because some animal cells grow and CO2 atmosphere. So different gases. So all these are called utilities. So when you are designing a downstream, we need to consider all these aspects as well. Okay. So many downstream processes, filtration, removing a solid from a slurry. That's called filtration. Different types of filtration. Sedimentation, again, you allow the solids to settle down. So all these two techniques are based on the size of the particle. So larger particles settle down nicely, smaller particles don't settle as much, and so on. So I have filters of different pore size, different diameters of pores. So when you have larger particles, they get stopped, smaller particles pass through. So they are based on the principle of size of the particle. Then we have chromatography, like gel permeation chromatography. Again, it's based on size or molecular weight. Okay, that's gel permeation chromatography, gel filtration chromatography. So this is the principle is the size. Centrifugation, cyclone separation, they are all based on the density of the material. Of course, particle size also comes into the picture, but density plays a very important role. When we talk about the precipitation, denaturization of the proteins, then temperature plays an important role. So when I heat it, proteins which can denature faster will lose its activity. So they will agglomerate and settle down. So if I have proteins which are more stable, thermally more stable, it will remain in the same state. So that is one way of separating proteins, mixtures. Crystallization. Of course, this depends upon the solubility of various solids. Temperature plays a very important role. So you have a saturated solution, you reduce the temperature, so the solution becomes super saturated, and then the material starts slowly crystallizing, and then it falls down, okay, or settles down as a solid and liquid, or it separates out. So solubility plays a very important role in this crystallization process. Liquid extraction. This is again used quite widely in downstream because you can operate it at room temperature. So we can use ethyl acetate, we can use methanol, ethanol. You can use liquid extraction for separating metabolites like acetic acid, or we can use it for removing even proteins. I talked about the reverse micellar extraction, where I'm using a surfactant. Although I use a solvent, the protein doesn't get denatured because I have surfactants which capture the protein and maintain it in polar environment. Okay, so I can use liquid extraction, aqueous two-phase extraction, reverse micellar extraction for removing metabolites, proteins, biomolecules, peptides. So partition coefficient plays a very important role in this particular situation. Then comes adsorption. This is a surface phenomena. We have gases getting adsorbed on solids. Okay, so generally adsorption is not used too much in bioprocess, but of course it's used when you're talking about venting out gases. So if you have any toxic gases, you can remove that by using activated carbon or silica or zeolite or alumina and so on. Then comes distillation. And distillation is used widely in chemical engineering because the small molecules are not thermally sensitive, so we can distill. We can remove them because of the difference in their boiling points or difference in their pressure. It's cheap, it's well understood, it's been there for hundreds of years. So there are distillation columns which can separate out mixtures of liquids. Okay, but distillation is not used too much in biological situation because biomolecules cannot adjust for such high temperature. Of course, if you are using a liquid extraction and the solvent you want to recover, so you may resort to distillation. That is, after removing your protein, then you may resort to some distillation to recover the solvent. Okay, that is the only situation where you use distillation. Otherwise, we don't use distillation much in bioprocess. Then comes drying. Basically, you are talking about evaporation of the vapor. Drying, if you're solid, if your product is a solid, then you resort to drying. And of course, drying temperature may go to 60, 70, 80. So if it's a pharmaceutical product, drying is widely used. But if you're talking about immobilized enzymes, it's not a good idea to use drying because temperature can go up. So in such situations, they go for lyophilization. Lyophilization is done at low temperature. That's a sublimation process. Okay, so for example, purifying and storing red blood corpuscles. Okay, lyophilization is used. So you do it at low temperature by sublimation. So if you're talking about biosystems, then you resort to lyophilization rather than drying. Whereas if it's a pharmaceutical product, it's a small molecule, then drying can be used. Of course, drying is cheaper than lyophilization, much cheaper, because in lyophilization you are reducing the temperature. So whereas in drying you are heating, so drying is much cheaper. Then comes dialysis. Dialysis, as you know, is widely used nowadays for those who have renal problem. That means those whose kidney stop functioning efficiently. Kidney helps a person to remove salts from the blood, okay, creatinine, uric acid, and so on. But if the kidney stops functioning efficiently, then they resort to something called dialysis. This is based on a membrane process. Okay, so the salt concentration in the blood side would be high, so it diffuses into the dialysate where salt concentration is low, so it's based on fixed law of diffusion, so it directly flows in, and as it passes the dialysate in a tube, inside of the tube, and outside you have the blood or vice versa. Okay, then what happens is the salt concentration starts going down from the blood region into the dialysate region. Okay, so this is based on diffusion. Okay, concentration gradient flow. Okay, that's how dialysis works, and it's a membrane based process. Electrodialysis, of course, it's also a membrane-based process. We apply an electric field, as the name implies. You know, here we apply an electric field, so the ions move towards the anode or the cathode, depending upon the nature of the charge. So we can use electrodialysis for purifying brackish water, salt water into very pure water. And we can use it for removing salts from mixture of protein, salt. Okay, so alternate compartments will have salt, other compartments will have the pure protein. Of course, it consumes electricity, so we need to have this facility where electricity is available in plentiful, or especially near the places where they generate electricity, and especially in the nights there could be excess electrical energy available. Then they can use that energy for running electrodialysis plants. Okay, so it's a combination of membrane and it's a combination of molecular interaction and electric forces. Then comes affinity chromatography. So here we have a ligand which is immobilized, and it captures the protein or enzyme which has a direct interacting. The active side of the protein or enzyme is exactly complementing to the ligand. That's called affinity chromatography. Okay, so it's very accurate. It's very selective. There will be only one type of enzyme which can go and bind to that ligand. So only those enzymes are captured, whereas other enzymes are not captured. So it's extremely it's an extremely powerful technique for purifying material to 99 plus purity. Okay, then comes reverse phase chromatography. This is based on the hydrophobic interactions. So as you know, proteins have hydrophobic amino acids. So some proteins are very hydrophobic, some are moderately, and so on. So the column material interacts with the protein. So hydrophilic proteins will come out first. Hydrophobic proteins relatively will slowly start coming out. So this is called a reverse phase chromatography. This is again widely used in biological situation. Then come ion exchange chromatography. So if you want to remove salts, we can use ion exchange. If you have proteins of certain charge, again we can have complementary charge immobilized on the stationary phase, then that's called ion exchange. So we can have anion exchange chromatography, cation exchange chromatography, or mixed ion exchange. So generally, if you go to a bioprocess, you will see two chromatographies running one after another. So initially you may have ion exchange chromatography to remove the ions, then you may go into the say gel filtration if the proteins have to be removed based on the molecular weight, or you may go for gel filtration, then you may go for affinity if you want very, very high purity material. Okay, or you may go for reverse phase, then you may go for affinity. So you may have a couple of chromatographies running one after another so that you get very high purity. So generally affinity chromatography will be the last chromatography because as I said, it's very selective interaction between the ligand and the protein and the enzyme. So we get very pure material, the enzyme, whereas the other enzymes which do not have the complementary size and shape as the ligand will not bind, so they escape the column. Then reverse osmotic membrane, this based on osmotic pressure, that's RO situation, RO membrane. Now this is used if you are interested in removing salt from brackish water, or removing salt from the seawater. So it's based on pressure. Okay, whereas electrodialysis is based on electrical charge, and membrane. RO is based on applying an osmotic pressure in the opposite direction, larger than the osmotic pressure, so that pure water flows from salt water into the pure water chamber. So that is why this is called reverse osmotic membrane. Then comes peroperation. This is again a membrane process. It's a combination of permeation and vaporization. So initially you do a vaporization. So you are the liquid or the solvent gets vaporized by applying little heat and a lot of vacuum. Then they permeate through a membrane which does not have any pores. So peroperation membrane, the movement of the solute is by diffusion. So if two solutes have different diffusion rates or different diffusion coefficients, so you can separate them based on their differences in their diffusion coefficient. Okay, of course these are various techniques. Now look at this. This is manufacture of recombinant insulin. As you can see here, a lot of steps are there. Okay, it contains okay, a lot of steps. We are digesting the enzyme because your product is inside. Your product is inside. It's an intracellular product. Then we sonicate it. We use detergents. Then we go get screwed protein, and then what we do is we remove the cell debris. Okay, then what we do, the protein lost its activity because of cell breakage and digestion using all these techniques. So it has to be refolded. First it has to be fully unfolded, and then it has to be refolded. That's what is done here. So there are many downstream things that happen here. It's initially you collect the cells. That means you harvest the cells, and then you break the cells, and then you remove the cell debris. Then you do a lot of biotransformation. You unfold the protein. That means you break some of the chains so that it gets fully unfolded. Again, you form the chains and you get the tertiary structure back. That's called the refolding. So all these things happen when we talk about a particular product called recombinant insulin. And then finally, you need to do a lot of purification so that you get your product at very high purity, because we are talking about some pharmaceutical product which is going to be used by the human. Okay. So we covered a lot of things in the course. If you can recollect, we looked at a lot of different flow sheets, the metabolites related flow sheet. That means small molecule like ethanol. Those are all metabolites, acetic acid. And then we also looked at flow sheets which involve biomolecule, like your insulin and so on. Okay, then we looked at mass and heat balance because they are very, very important. Mass balance, what is heat balance? We need to understand for each of the unit operation, we need to know what are the various streams that are coming in, and what is happening to the material that's going out. So how do they get partitioned and so on actually. So mass and heat balance we looked at. Then we looked at costing. Like I said, costing is very important. We looked at equipment costing, we looked at operating cost, and we also said that we can look at selection of equipments based on cost. For example, should I go for a centrifuge or should I go for a filter? Filter may be cheaper than centrifuge, of course, but recovery is better in centrifuge. So if your product recovery and cost of the product is very high, like if it's a very highly value added product, it's a high cost product, then I would like to recover as much of material as possible. So centrifuge, you may have to put in more money initially, but later on you may recover more profit because your cost of the product. So costing is one technique by which you can make selections, like if you have a centrifuge versus filter, or if you want to do a liquid extraction vis-a-vis something else like a chromatography. So when you have that sort of choice, then which one do I go for? We need to think in that line. Then comes cell disruption. If it's an intracellular product, we talk about cell disruption, right? So different types of cell disruption: mechanical, chemical, enzymatic, thermal. Okay, so all these methods we talked about. Okay? Advantages, disadvantages of various techniques, and what are the equations involved in that, whether we can design like how long you need to run a homogenizer to get 80% of the protein or 90% of the protein, and what are the parameters that needs to be thought of, and all these we discussed in the cell disruption. Then came solid liquid separation. So different types of techniques are there. We talk about, there is sedimentation, there is coagulation, and there is settling, then there is filtration, there is centrifugation. So all these techniques all deal with solid liquid separation. Then we looked at the design equation like Darcy's law. We also looked at what happens if the solid bed is compressible. That means if the bed gets tighter and tighter, if you keep increasing the pressure, the flow of the liquid will become poorer and poorer. So what happens in such situations? How do you modify the design by adding filter aids so that the bed doesn't get compressed? So we looked at the solid liquid separation. That is one thing. Then we looked at centrifugation, different types of centrifuges, and then how to have design equation for centrifuge. How do you connect when you talk about scale up? And we said two important things happen in centrifuge. One is related to the settling time, that means the solid and liquid properties. Other one is related to the hardware details. So how can we talk about scaling up of this particular centrifuge? Okay, then in filtration, we looked at something called Darcy's law, how we can use Darcy's law to calculate time for filtering a certain amount of slurry for a given area of cross section. Okay, so if I change the pressure, what happens to the time? If I change the compressibility, what happens to the time? So we looked at all those equation based approach when we talked about designing a filter. Then came extraction, different types of extraction. We talked about liquid extraction, then reverse micellar extraction. Then we talked about aqueous to phase extraction. Okay, then in extraction, how do we go about designing? How many stages of extractors do we require? If there is a cross flow situation, if there is a counter current flow situation. So given the number of stages, how to calculate the efficiency of extraction, or for a desired efficiency, how to calculate the number of stages. So we did all those calculations. We looked at the efficiency factor, and so detailed calculations were done. Then we also looked at the aqueous two-phase extraction. What are the design equations involved? We talked about the upper phase and the lower phase, and based on the partition coefficient, how to design, understand the yield, and so on. And then looked at adsorption using solid adsorbent. How do you start recovering the solute? What is the efficiency of the adsorption process if you have a certain amount of adsorbent added? If I do it in one stage or if I do it in two stages, how does it change? We also looked at different types of adsorption isotherms like linear, Freundlich isotherm, and then okay, Langmuir isotherm. So each isotherm, we looked at those equations involved, and we also designed based on the mass balance and based on the equilibrium relationship, the calculating the efficiency of adsorption as well as the number of stages required for adsorption. Then came, of course, liquid extraction. The liquid extraction, like I said before, we looked quite a lot about the design equations, number of stages calculations, efficiency, how much solvent required for extraction, and so on actually. And again, in the aqueous two-phase extraction, we looked at how much of upper and lower phases concentrations of the desired product is, and what is the partition coefficient, and so on actually. Then in membrane separation, we looked at different types of membranes: ultrafiltration, nanofiltration, microfiltration, then reverse osmosis dialysis, electrodialysis, then pervaporation, different types of membrane processes, the flow of the liquid through the membrane, okay, how to calculate, looking at permeability, and so on. Then came precipitation and crystallization, how the crystal starts growing, like the McCabe law we looked at. What is the rate of crystal growth based on the size? Okay, then precipitation. What are the advantages and disadvantages of precipitation? Then we looked at drying. This is a technique, especially at used to remove moisture at higher temperature, whereas here we talk about through sublimation, removing moisture at lower temperature through sublimation. Stabilization, bioproducts can get oxidized, or they can have bacterial contamination. So generally a lot of other chemicals are added, or other enzymes are added to stabilize. As you know, enzymes can lose activity, so enzymes could be immobilized, or enzymes could be encapsulated. They are all called stabilization. A lot of these, and especially when you talk about when we are dealing with biological systems, stabilization plays a very important role, because they can lose activity because of contamination, because of pH changes, because of thermal changes, because of oxidation, because of reactive oxygen species. So stabilization is a very important technique. Then comes electrophoresis and okay, SDS page type of techniques, where you apply charge, and the proteins move based on their charge, as well as their the diffusion coefficient. Diffusion coefficient inversely is related to the size of the protein. Okay, so we can separate out proteins of different charges, proteins of different diffusion coefficients or sizes, using this type of technique. Then looked at chromatography, large number of chromatographies, the types, the principles, the equations involved, how to calculate number of theoretical plates, how to calculate the efficiency of separation, and all these we looked at in very detail in the area of chromatography. Then little bit on the future trends, how the downstream science is going to move, what are the issues that needs to be addressed, and how the industries are looking at downstream. So we looked at that future trends. So this is very important because if one wants to go into a research in the area of downstream, it's good to know where I would like to go in that area of research. Okay, so if you let me touch a little bit upon the future, the top concern of the industry, that is cost of chromatography. Because as you know, chromatography, different types of chromatographies are used in industrial situation, especially for pharmaceutical products, and they cost a lot of money because you are going to use some solvents as the mobile phase. You are going to use a lot of stationary phase material, which although you can recycle a little bit, after few recycles they are not going to last, so you need to throw them out. So cost of the packing material, cost of solvent, you can recover some amount of solvent, but then you can't recover all the solvent, right? So that's an issue. Then comes there was some industry survey done, and they tried to find out which downstream will cause bottleneck in the future, and it was found a column chromatography. See, as you can see, chromatography, virus removal, because most of the antibiotics, many products are now still based on bacterial systems. So there could be some worry that whether you have removed all the bacteria or a little bit of bacterial contamination may be coming into the final product. So that's an important point. Then ultrafiltration, that's another point. Depth filtration, tangential flow filtration. So you can see a lot of filtration involved. Clarification, sterile filtration, diafiltration. So all these are filtration based material. So they are going to cause big bottleneck. So chromatography, that comes the top. Then how sure you are that you are removing all the bacterial contamination, which bacteria which is used for manufacturing your antibiotics or any product. And then filtration, different types of filtration, they are going to be the real bottleneck, because as I mentioned that compressibility is a big issue. So you need to keep you need to stop the filtration and remove the material that's deposited. Then okay, solid buildup. Okay, these are some big issues. And then the membrane or the filter cloth you need to replace from time to time, that's going to add to the cost. So all these are issues related to filtration. Okay, sometimes the biomass will start growing as a function of time, so you need to be sure to remove that biomass. So all these are some issues that needs to be addressed. So that is why they are going to be the bottleneck in the future. Okay, okay. There is a lot of interest nowadays in single-use equipment, disposable equipment. So now many companies have started making even bioreactors, which are made up of high-density polyethylene. So you use it once and then throw them out. Even 50 liters, 100 liters, 200 liters, 500 liters, with the air inlet, feed addition, okay, thermal temperature measurements. All these are being now done with the disposable bag type of bioreactors, because the advantage is you don't have to bother about contamination. If you have a stainless steel or a glass vessel, after one particular product, if you are going to switch to some other product, you may be worried what will happen. Will there be contamination? You may have to clean many times, especially FDA related issues. So single use equipments, we don't have to bother about that. Okay, so modular, so we can mobile, so we can move your chromatography unit from one place to another and then do the job again, move it back. So many of the operations can be have mobile, modular. Okay, plug and play with disposable components. So I just buy a disposable bioreactor, a disposable for chromatography column, then do the job and throw them. So I don't have to think about will there be contamination, how many times I wash so that I am sure there are no impurities or side products left behind from the previous batch. All these can be avoided. So there is going to be a lot of interest in the long run. As I said, nowadays large-sized bioreactors with a lot of input measurements and raw material additions are now coming into market. So we don't have to bother in the long run for having a fixed metal or a glass-based reactor system. Okay, so based on what we have spent over the past so many weeks, we can say downstream process is an interdisciplinary subject. It connects engineering, protein, biochemistry, biology, analytical chemistry, and biochemistry. And the economics of the process is completely based on downstream. Because 60-70% of the total cost of the product could be because of downstream. As I said, chromatographies are very expensive. So if you have many chromatography steps, then you are going to have your product cost shooting up. Whereas if you have very simple steps, then your product cost would be very low. So downstream is going to play and decide on the economics of the bioprocess. So it's very, very important for us to understand the downstream, and it's very, very important for us to optimize the design of the downstream equipment, optimize the batch cycle time, operating conditions, so you have very economical downstream steps. Okay, so we talked quite a lot, and I thought I will talk a little bit on some of the recent techniques, because there has been some questions on can we touch upon those recent techniques. Okay, before that, let me also give you a slide on possible references. If you are interested, bioseparations, Welter Kessler Handbook of Downstream Processing, Goldberg, Bioseparation Bioprocess, 2-volume set, Nasenjo, Separation Process Biotechnology, Bioseparation Engineering, Principles of Downstream Techniques. So all these are very useful books. It's nice to have them in your library for reference purposes as well. Okay, so let me touch a little bit on two very modern techniques where I have not spent much time in the course. Okay, one is called the aqueous two-phase extraction. Although I touched a little bit on aqueous two-phase extraction, I'll spend a little bit because somebody had asked a question. Partition of solute between two water-rich phases. Generally, the amount of water is very large, because generally we use a solvent to extract a product from a fermentation broth, which is predominantly water. But here we are using water itself to extract a protein from a water. Okay, that's the challenge of this. So 85% will be water. So it could be a polymer system, or it could be a polymer salt system. So polymer. So one phase will have a polyethylene glycol. Another phase could have dextran of various molecular weights and quantity. And so there is a separation that's taking place of the biomolecule from one phase to another, or a PEG pullalan, PEG polyvinyl alcohol, PEG hydroxypropyl. And if I increase the molecular weight of PEG, then the solubility of the protein may be going down and it may go to the other phase. If you look at polymer salt system, we have PEG phosphate, PEG citrate, PEG sulfate. Okay, so if I keep increasing the salt amount, of course, there is a salting out happening. So it may, the product desired biomolecule may be going into the PEG. So if I maintain PEG molecular weight to be low, and if I add a lot of salt, then the biomolecule may salt out and go into the PEG rich phase. So two approaches by which aqueous two-phase systems work. One is based on polymer system, the other one is based on polymer salt system. Okay, so the partition coefficient K is defined as concentration of the protein in the top phase, that is light phase, concentration of the protein in the bottom phase. That's called the heavy phase. Okay, light phase, heavy phase. If K is large, of course, the numerator is large, so protein tries to go more in the upper phase. If K is less than 1, then protein tries to go more in the lower phase. So K remains constant for a wide range of polymer concentration. And this is a very interesting diagram for the aqueous to phase. This is a phase diagram, okay? And this is called the tie line. This is a phase diagram. So in this axis, x-axis, we may have polymer A, y-axis you may have polymer B, or x-axis you may have salt, and y-axis you may have polymer, weight per weight, okay? And generally this line, okay, this line separates the monophase to the biphase, okay? So if I take say this concentration, okay, below this region, the entire system is in a single phase system, whereas above this it's a biphasic system, okay? So you get good separations. Above this you will be able to separate them, whereas below this it's in a single phase, so you will not be able to separate out. Okay, this is called a phase diagram. This is called a tie line. Okay. Now, I picked up this from this very interesting reference. So somebody who is more interested can read this particular review article, okay, to understand more about this aqueous two-phase system. Okay, they have given a nice example. Look at this. This is a salt, concentration of salt, the weight per weight, and concentration of PEG, weight per weight. Okay, so we get this particular okay, equilibrium relation, below which we have the single phase, above which we have the two phases, okay? And so this is called the tie line. This is called the tie line. Again, the units is a percentage W per W. So where the tie line intersects with this particular graph, this particular curve, this place is called the concentration of PEG in the top phase, okay, and correspondingly here concentration of salt in the top phase. And this place, if you take it here, this is the concentration of PEG in the bottom phase, concentration of the salt in the bottom phase, okay? So where this particular line, tie line, intersects with this equilibrium graph, we can read out the concentration of PEG in the top, concentration of salt in the top, concentration of PEG in the bottom, concentration of salt in the bottom, okay? So how do you draw this tie line? Okay, the tie line, it's got a slope, okay, it's got a length. The length is given by this particular relationship, as you can see, B salt minus T salt square. This is the equation of a straight line, right? B salt minus T salt square plus T peg minus B peg T peg minus B peg square, and then you take a square root, and that will give you the length of this tie line. Slope of the tie line is given by T peg minus B peg divided by B salt minus T salt. Okay, so we have both the length and we have the slope from this relationship. So as the tie, if you keep bringing the tie line closer, at one point, okay, and there is no difference in the concentration of the salt and the PEG in the top and the bottom phase, and that's called the critical point. So you don't like to operate at the critical point because you will not get separation, or you will not see a difference in the concentration of PEG and the salt in the top and the bottom phase. Okay, so ideally you would like to operate. So if you look at these points X, Y, Z, okay, it may be the total concentration of PEG, they're all same, but the concentration of the PEG and salt in the top, as well as the concentration of PEG and salt in the bottom, are different for these particular points. Okay, as you can see, X, Y, Z, concentration of PEG in the top, the concentration of PEG in the bottom, and the concentration of salt in the top and the concentration of salt in the bottom are very different. So if you take this Z point here, this will have okay, more salt As you can see here, this is just a representation, whereas if you look at this point, it will have less salt in the bottom phase, and so on actually. Okay, so this is how you can develop your relationship, and you can get the concentration values from the intersection points. Okay, there are many equations for fitting this graph also. Broadly, okay, so the system XYZ differs in their initial composition and the volume share, but they all have the same top phase equilibrium composition Tpex T salt, okay, Dpeg D salt. Okay, the concentrations are the same. The initial compositions may be varying, but because they go and intersect there. Two important correlations: Othmer, Tobias, and Bancroft equations, which are used to fit the tie line data. Okay, these two references nicely give those informations. Okay, so you can fit we can fit this using these type of relationships. So we can calculate K value, we can calculate N value, or we can calculate K1 and we can calculate L1. These references will give more details about other types of equations which are available for fitting these equilibrium relationship and so on. And of course, like I said, this reference will give you more information on this particular aqueous to phase extraction system, and what are the implications of the tie line and slope of the tie line and so on actually. Okay, so there is more interest nowadays in aqueous two phase extraction because predominantly it contains water, and it will contain it may contain two different polymers, or it may contain one polymer and a salt. So if the polymer molecular weight is high, protein solubility goes down, so it may move to another phase. And if you have excess of salt, then protein solubility goes down, so it gets salted out. So that's the principle of this particular method. Another interesting newer technique that's slowly coming in the past 15 years, I would call it the simulated moving bed chromatography. Okay, there are a lot of disadvantages of the current chromatography, and hence this simulated moving bed chromatography is trying to overcome that particular problems. Okay, so it basically uses multiple smaller columns containing solid adsorbent rather than one large column. Okay, so the one large column method is we put in the feed and then you get one product after another. So it's more like a linear, whereas the simulated movement, as if the bed itself is moving, overcomes these problems. So you use less solvent, we can start getting all products simultaneously, and that's the advantage of the simulated moving bed chromatography. So if you look at the conventional chromatography, the solvent is added here. Suppose we have A and B, we add here. So there is a packed bed and your product keeps coming down. B has more affinity to the stationary phase, so A has less affinity, so A will come faster. We collect all the A, and after some time B will come, we collect all the B. So it's very linear process. Okay, you will not be collecting B at all. So if you have A, B, C, D, you will collect A first, B next, C next, D next, and so on. So a lot of bed is unutilized by this. So how to overcome this problem? That's what the simulated technique came into being. Suppose we have feed entering here, AB, solvent is entering here, and imagine the bed is moving in this direction. Okay, because B has more affinity to the stationary phase, A has less affinity. A will start coming here, B will start coming here. Okay, so suppose you have a long column and the bed is moving, so B sort of getting captured with the bed, so it moves forward, so B comes down here and A comes down here. So there is an advantage because you can continuously collect B, continuously collect A, continuously feed, continuously add solvent, unlike your original method where it's more like a batch process. Okay. The disadvantage is if you have a linear column, that means you need an infinite column. No, you have to keep on introducing again column packing in the side and removing. So what they did was they considered a circular system like this. Okay, they considered a circular system and so it is like a column, new column entering and old column leaving. So we have a feed A and B, solvent is introduced, bed is moving in this direction. So of course B will start coming out here, A which has less affinity will start coming out here. Okay, so this is a fantastic approach because we have overcome the linearity and we are using all the column parts, and you can continuously collect A, B, and you can continuously feed A and B, and we can have continuous solvent input. Okay, even this has a little bit disadvantage because we need to have bed moving, and we need to have these inputs, inlets, pipes able to take care of the movement of the bed. So engineering issues are there. So they try to overcome that in another way, interesting way. So what you do is, instead of moving the bed, you move the inlet and outlet ports. Okay, that is equivalent to moving the bed. Okay, so bed is stationary here. So again, you have feed A, B, solvent here, A coming here, B, sorry, A going out here, B going out here. But then after some time, you move this. So the opening for B is slightly clocked up, feed AB goes up, A goes up. So this is equivalent to moving the bed in a counterclockwise direction in the previous case. Okay, so instead of moving the bed, you move the openings. And then again you move, so the B has come here, and the feed A, B has come here, and A has come here, the solvent. So you keep on doing that. So the advantage is you continuously collect B, you continuously collect A, you can continuously feed A and B, and you can continuous input solvent. So this becomes a continuous operation. So the entire bed is being used, unlike a linear approach. Unlike a linear approach, which is not very efficient. Bed is unutilized, B is collected only after A has been completely collected, and it's a more like a batch process. So this is coming slowly into market, where now I showed you an example of two components, so two outlets. We can even have many outlets. So if you are interested in some 4 or 5 or 6 components, you can have 6 or outlets, and continuously these outlets move, not the bed, but the outlets move in a clockwise direction in a step manner. So we collect the product. Okay, so you can continuously collect the product, and you can continuously feed the mixture. So the simulated moving bed has many advantages over the traditional conventional approach, and I'm sure in the near future we will be replacing the conventional chromatography. And another other advantage is, unlike in the linear, you do not use most of the column packing, but here you will be using the column packing very efficiently. Okay, so I'm sure this type of new research angles will improve the chromatography operations and improve the efficiency of the chromatography. Okay, so these are some new techniques that's being researched on, and new engineering concepts that are being looked at. And I'm sure in the next few years, we will see industrial scale simulated moving bed chromatography and industrial scale phase-to-phase extraction techniques being practiced quite a lot. Okay, so to conclude, I hope you enjoyed this course over the period of 5 weeks, and you get a flavor of the downstream techniques that are being practiced as of today in industrial scale, how to go about designing the various equipments, calculating cycle time, designing number of stages in an extractor or a chromatography unit. And as you can see, it's highly interdisciplinary. We need to understand not only biochemistry, we need to understand a lot of engineering principles. I brought in some concepts of costing, which is not being taught anywhere. So how to decide on equipment selection based on cost factors. Okay, so examination is also going to be almost like your quizzes. You will have 1 mark questions, you'll have 2 mark questions, and 4 or 5 mark questions. Some of them will be multiple choice, and some of them will be writing the answers. And the problems which we have looked at in the presentations or the videos, as well as the problems that are being given in your quizzes, will be exactly followed in the final exam also. I hope you benefited from this course, and hope to hear from you soon after the exam. Okay, thank you very much. All the best to you.